Every sunrise feels familiar, yet the glowing star above us is a place more violent than anything on Earth. There's a particular kind of comfort in the sun's presence, one so constant and so deeply woven into daily life that most of us rarely pause to consider it at all. It rises each morning without announcement, warms the air, wakes the birds, and slips quietly below the horizon each evening, only to return again the next day, exactly as it has every single day of every human life that has ever been lived. This unwavering reliability has made the sun perhaps the most overlooked object in the entire sky, so familiar that its true nature has become almost invisible to us, hidden in plain sight behind the simple, golden warmth we feel on our skin. And yet this sense of familiarity is, in many ways, an illusion, one built entirely from distance and safety, rather than any genuine similarity between the sun and the quiet, stable world we call home. The sun is not a gentle, glowing lamp hung conveniently in our sky. It is an enormous, churning sphere of plasma, a star in the truest and most complete sense of the word, bound together by its own immense gravity and powered by a process so extreme that it converts matter itself into pure, radiant energy at its very core. Standing beneath its light, we experience only the faintest, most distant echo of the almost incomprehensible violence occurring within it at every single moment. To grasp even a small sense of the sun's true scale, consider this. Earth, the world that contains every mountain range, every ocean, every city, and every person who has ever lived, could fit inside the sun more than 1 million times over. The sun accounts for more than 99% of the entire mass of our solar system combined, a single object so overwhelmingly dominant that every planet, moon, asteroid, and comet orbiting it together amounts to little more than a faint gravitational afterthought by comparison. Every planet we have explored throughout this channel's documentaries, from Neptune's supersonic winds to Mars's ancient vanished rivers, owes its very existence, its orbit, its warmth, and in many cases its entire history, to this single, enormous star at the center of it all. The importance of the sun extends far beyond simply providing light and warmth, though these alone would be reason enough for its significance. The sun's gravity is the invisible architecture holding our entire solar system together, the silent force that has guided the orbits of every planet since their earliest formation billions of years ago. Its energy drives Earth's weather patterns, powers the water cycle that fills our rivers and oceans, and provides, both directly and indirectly, nearly all of the energy that has ever sustained life on our planet, from the first microscopic organisms in ancient oceans to every forest, every harvest, and every meal eaten by every person throughout human history. This documentary is an invitation to look at the sun differently than we typically do, not as a familiar backdrop to daily life, but as what it truly is. An active, dynamic, and genuinely extraordinary object, one that continues to surprise scientists even after centuries of dedicated study. We will travel from the vast cloud of stardust from which the sun was born, down into the crushing heat of its nuclear core, out through layers of plasma more violent and unpredictable than anything found on any planet, and finally forward across billions of years into a future that will eventually transform the sun itself into something almost unrecognizable. Along the way, we will explore how humanity has gradually come to understand the star, from ancient civilizations who worshipped it as a god, to the sophisticated spacecraft now flying directly through its outer atmosphere, gathering data once thought entirely impossible to obtain. Long before any of this scientific understanding existed, humanity's relationship with the sun was shaped almost entirely through observation, reverence, and necessity. Ancient civilizations across the world independently recognized the sun's central importance to life itself, building entire belief systems, calendars, and monuments around its steady, predictable movement across the sky. The rhythm of planting and harvest, the changing of seasons, the very structure of daily life itself, all depended on a careful, patient understanding of the sun's behavior, developed long before anyone possessed the scientific tools necessary to understand what the sun actually was. This ancient reverence, though built without the benefit of modern science, was not entirely misplaced. The instinct to view the sun as something worthy of deep respect and careful attention reflects, in its own way, a genuine truth that science has only more recently come to fully confirm. The sun is not merely a convenient source of daylight. It is the singular, irreplaceable engine sustaining nearly everything we recognize as life on Earth. A star whose steady, reliable output across billions of years has allowed something as remarkable and improbable as complex life to emerge, evolve, and eventually develop the curiosity necessary to study the very star that made its own existence possible. As we begin this journey together, it is worth setting aside, at least for a moment, the familiar, comfortable image of the sun as simply a warm light in the daytime sky. In its place, we will gradually build a far more accurate picture, one that reveals a star of staggering scale, tremendous internal violence, and remarkable complexity. A nuclear furnace powerful enough to sustain almost unimaginable output for billions of years, yet stable and consistent enough to have made life on Earth possible in the first place. But to truly understand the sun as it exists today, we must first return to the very beginning, to a moment long before it ever began to shine, when it existed not as a star at all, but as nothing more than a vast, cold, and quiet cloud of scattered dust and gas, drifting slowly through the darkness of space. To understand what the sun has become, we first need to return to its birth. Roughly 4.5 billion years ago, in a region of space no different in appearance from countless others scattered throughout our galaxy, there existed nothing that resembled a star at all. Instead, there drifted a vast, cold cloud of gas and dust, spread out across many trillions of kilometers, composed primarily of hydrogen and helium left over from the earliest moments of the universe, mixed together with trace amounts of heavier elements forged within the cores of earlier generations of stars that had lived, aged, and eventually died long before our own sun ever began to form. Astronomers refer to this vast, diffuse structure as a solar nebula, a term that captures both its enormous scale and its eventual destiny. For a long period of cosmic time, this particular cloud remained largely stable, its scattered particles of gas and dust drifting slowly under the weak, gentle pull of their own mutual gravity, a force present but not yet strong enough to trigger any dramatic transformation. Clouds like this exist throughout our galaxy even today, vast, quiet nurseries of potential stars, waiting patiently for the right conditions to finally set their formation into motion. For our particular solar nebula, that necessary trigger is believed to have arrived from beyond the cloud itself, quite possibly in the form of a shockwave traveling outward from a nearby supernova, the explosive death of a massive star that had lived out its own dramatic life cycle somewhere nearby. This shockwave sweeping through the quiet, drifting cloud would have compressed certain regions of gas and dust more tightly together, disturbing the delicate balance that had allowed the cloud to remain stable for so long, and setting into motion the gradual gravitational collapse that would eventually give birth to our entire solar system. As gravity began pulling these newly compressed regions of gas and dust more tightly inward, the cloud started to collapse, slowly at first, then with steadily increasing speed as the process gained momentum. Like a spinning ice skater who speeds up their rotation by pulling their arms inward, this collapsing cloud began spinning faster and faster as it contracted, eventually flattening into a broad, rotating disk, with the vast majority of its material gradually gathering into a single, increasingly dense concentration at the very center. This dense central concentration, growing steadily hotter and more compressed as additional material continued falling inward under gravity's persistent pull, is what astronomers call a protostar, an early, still-forming stage of stellar development that exists somewhere between a simple cloud of gas and a genuine, fully formed star. During this protostar phase, our young sun had not yet begun generating energy through nuclear fusion, the process that would eventually define it as a true star. Instead, its growing warmth came almost entirely from the sheer gravitational energy released as additional surrounding material continued collapsing inward. compressing the protostar's core to increasingly extreme temperatures and pressures with each passing 1,000 years. This process of gradual gravitational collapse continued for a substantial period, roughly 100,000 years by most current scientific estimates, a relatively brief span of time when measured against the Sun's eventual multi-billion-year lifespan, yet still representing an immense stretch of time by any ordinary human measure. Throughout this period, the young protostar continued growing steadily hotter and denser at its core, drawing ever closer to the critical threshold that would finally transform it from a simply warm, collapsing cloud of gas into something entirely new. That threshold was finally crossed when core temperatures climbed high enough and pressures grew extreme enough to trigger nuclear fusion, the process through which hydrogen atoms begin fusing together to form helium, releasing tremendous quantities of energy in the process, a topic we will explore in far greater detail throughout the next chapter of this documentary. The moment this fusion process ignited within the young sun's core marked the true birth of our star, the precise instant when a slowly collapsing cloud of gas finally became something capable of generating its own light and energy, entirely independent from the gravitational collapse that had brought it into being in the first place. While the vast majority of material within the original solar nebula gathered together to form the Sun itself, a small but significant remaining portion continued swirling within the broad, flattened disk surrounding this newly formed star, material that would eventually give rise to every planet, moon, and smaller body within our entire solar system. Within this surrounding disk, the same basic processes of gradual accumulation that we explored in considerable detail throughout our earlier documentary on Mars, and briefly touched upon regarding Neptune's own formation, began steadily building larger and larger bodies from smaller grains of dust and ice, eventually giving rise to the planets we recognize and continue exploring today. This shared origin carries genuinely profound significance, one worth pausing to fully appreciate. Every planet within our solar system, from small, rocky Mercury orbiting closest to the Sun, to distant, windswept Neptune marking the outer edge of our planetary system, formed from the very same original cloud of gas and dust that gave rise to the Sun itself. In this sense, every planet we have explored throughout this channel's ongoing documentary series shares a common origin with the Sun, siblings born from the same collapsing cloud, shaped by the same fundamental physical processes, differing dramatically today only because of their varying distances from the central star and the particular mix of material available within their own specific region of that ancient, swirling disk. Following this dramatic period of formation, our young sun continued evolving gradually across its early history, slowly settling into the stable, consistent pattern of energy production that continues sustaining it today. Current scientific evidence suggests that the Sun's earliest years were considerably more turbulent and variable than its current, remarkably steady output might suggest, a period during which its brightness and overall energy output likely fluctuated more significantly than at any point since, gradually settling into the stable, predictable behavior that has defined its character for the vast majority of its now 4.5 billion year existence. This early period of relative instability carries important implications for understanding the early history of the planets that formed alongside the Sun, including the early, warmer conditions that may have once allowed liquid water to flow freely across the surface of Mars, a topic we explored extensively throughout our previous documentary. Some scientists believe that variations in the young Sun's energy output during this formative period may have played a meaningful role in shaping the early climate conditions experienced by Mars, Earth, and the other inner planets, adding yet another layer of connection between the Sun's own early history and the broader story of planetary formation and evolution that continues to unfold across our entire solar system. By the time this early, more turbulent period had finally settled, the Sun had become recognizably similar to the star we observe shining steadily above us today. A stable, reliable source of energy that would continue burning steadily for billions of years to come, patiently providing the light and warmth necessary to eventually allow complex life to emerge and flourish on at least one of the small, rocky worlds now orbiting quietly around it. For a brief moment in cosmic history, our sun was nothing more than scattered dust drifting silently through the darkness. What it became next would come to define the very possibility of life itself. At the very heart of the sun, buried beneath layer upon layer of dense, superheated plasma, lies a region unlike anywhere else within our entire solar system, a place where matter itself is transformed into pure energy at an almost incomprehensible rate, sustaining every flicker of sunlight that has ever reached Earth's surface. This is the sun's core, a region so extreme in both temperature and pressure that it stands as the single most powerful, continuously operating energy source anywhere within reach of human observation. To understand what makes this core so extraordinary, we must first understand the process occurring within it, a process known as nuclear fusion. At its most basic level, fusion involves forcing together the nuclei of individual atoms, combining them into a single, heavier atom in the process. Within the sun's core, this fusion process involves hydrogen, the simplest and most abundant element in the universe, with 4 individual hydrogen nuclei ultimately combining, through several intermediate steps, into a single nucleus of helium, the next element along the periodic table. This transformation from hydrogen into helium might initially sound like a relatively modest chemical rearrangement, yet the physical reality involved is anything but ordinary. When 4 hydrogen nuclei fuse together into helium, the resulting helium nucleus possesses very slightly less mass than the original 4 hydrogen nuclei combined. This small difference in mass does not simply vanish. Instead, following the fundamental relationship between mass and energy first described by Einstein's famous equation, this lost mass is converted directly into an enormous burst of pure energy, released outward from the core in the form of light and heat. The sheer scale of this ongoing process is genuinely difficult to comprehend using any ordinary, everyday comparison. Every single second, the sun's core fuses approximately 600 million tons of hydrogen into helium, releasing energy equivalent to detonating many billions of nuclear weapons simultaneously, every second, continuously, without pause, for billions of years running. And yet, despite this almost incomprehensible power, the sun does not explode or tear itself apart, held instead in careful, stable balance by its own immense gravity, which continuously works to compress the sun inward, precisely counterbalancing the outward pressure generated by this ongoing fusion process deep within its core. Achieving the specific conditions necessary to sustain this fusion process requires temperatures and pressures far beyond anything found naturally anywhere else within our solar system. At the very center of the sun's core, temperatures reach approximately 15 million degrees Celsius, a level of heat difficult to meaningfully compare to anything experienced in ordinary human life. Alongside this extreme heat, pressure within the core reaches levels roughly 250 billion times greater than the atmospheric pressure we experience here on Earth's surface. A combination of extreme heat and crushing pressure sufficient to force individual hydrogen nuclei close enough together to overcome their natural electrical repulsion and fuse together, despite the fact that under ordinary conditions, these positively charged particles would strongly repel one another rather than combining. This precise combination of extreme temperature and pressure exists only within a relatively small central region of the sun, a core extending outward roughly 1/4 of the sun's total radius. Beyond this central region, temperatures and pressures decline steadily with increasing distance from the center, eventually falling far too low to sustain any meaningful fusion activity. This means that despite the sun's enormous overall size, the vast majority of its total volume consists of material that, while certainly still extremely hot by any ordinary standard, does not itself directly participate in the fusion process, generating the sun's tremendous energy output. The sun's remarkable long-term stability depends entirely on a delicate, ongoing balance between two powerful, opposing forces, a balance scientists sometimes refer to as hydrostatic equilibrium. On one side of this balance, the sun's own immense gravity continuously pulls inward, working to compress the entire star into an increasingly dense, compact form. On the opposite side, the outward pressure generated by nuclear fusion within the core, along with the heat this fusion process continuously generates, pushes outward with equal and opposite force, precisely counterbalancing gravity's inward pull. This ongoing balance between gravity and fusion-generated pressure has remained remarkably stable throughout nearly the entire span of the Sun's 4.5 billion-year existence, allowing it to maintain a consistent size, temperature, and overall energy output across this almost incomprehensible span of time. Without this delicate balance, the Sun would either collapse rapidly inward under its own gravity, or alternatively expand rapidly outward under the pressure of unchecked fusion, neither outcome compatible with the kind of long-term, stable energy output that has allowed life on Earth the necessary time to emerge and gradually evolve into its current, remarkable diversity. It is worth pausing to appreciate just how essential this particular combination of stability and power truly is. A star significantly less massive than our Sun might never achieve sufficient core temperature and pressure to sustain fusion at all, remaining instead a failed star, sometimes called a brown dwarf, generating only a faint, residual glow rather than genuine, sustained nuclear fusion. Conversely, a star significantly more massive than our Sun would burn through its available hydrogen fuel considerably faster, sustaining a shorter, more volatile lifespan measured in mere millions of years, rather than the billions of years our own Sun has already enjoyed, and will likely continue enjoying well into the distant future. Our Sun occupies a particularly fortunate position within this broader range of stellar possibilities, massive enough to sustain stable, long-term nuclear fusion, yet not so massive as to burn through its hydrogen fuel too quickly, allowing it to shine with remarkable steadiness across a time span more than sufficient for complex life to gradually emerge and evolve here on Earth. This stability, so easily taken for granted given its consistency throughout the entirety of human history, represents in truth an extraordinarily delicate and finely balanced natural phenomenon, one occurring continuously, silently, and reliably at the very center of the star that makes our own existence possible. Yet the story of the Sun's energy does not end within this small, extraordinarily hot central core. The tremendous energy generated through fusion still faces an extraordinarily long, complex journey before it can finally escape the Sun entirely and begin its own separate voyage outward across space, eventually reaching Earth as the warm, familiar sunlight we experience each and every day. But where does this energy go once it is created, and how long does it take to finally escape? It seems at first like it should be a simple thing. Energy is created deep within the Sun's core through nuclear fusion, and light, being among the fastest phenomena in the entire universe, should presumably escape that core and reach the Sun's surface almost instantaneously. Yet the true story of how energy travels from the Sun's core to its outer surface reveals something genuinely surprising. A journey so slow and so obstructed that it stands in remarkable contrast to the same light's brief, nearly instantaneous journey once it finally does escape into the open space beyond. To understand this seemingly paradoxical journey, we must first appreciate just how extraordinarily dense and crowded the material surrounding the Sun's core truly is. Immediately beyond the core lies a region known as the radiative zone, an enormous layer of extremely hot, densely packed plasma extending outward for a considerable portion of the Sun's total radius. Within this radiative zone, individual photons, the fundamental particles of light generated through fusion within the core, do not simply travel in a straight, unobstructed line outward toward the surface, as sunlight does once it finally reaches the open vacuum of space. Instead, within this dense radiative zone, each individual photon travels only an extraordinarily short distance before colliding with a nearby particle, typically an electron, and being absorbed, then almost immediately re-emitted in a new, essentially random direction. This process then repeats itself again and again, with each newly emitted photon traveling only another brief distance before undergoing yet another absorption and re-emission, in a slow, chaotic, repeatedly interrupted journey that scientists sometimes compare to a random walk, moving forward, backward, and sideways in roughly equal measure, rather than progressing steadily and directly outward toward the sun's surface. Given the sheer density of material within this radiative zone, and the almost countless number of individual absorption and re-emission events each photon experiences along its winding path, the overall journey outward through this region proceeds at a genuinely astonishing pace, astonishingly slow, that is, rather than fast. Current scientific estimates suggest that an individual photon may require anywhere from tens of thousands to well over 100,000 years to finally complete its long, meandering journey through the radiative zone alone, despite the fact that light itself travels at the fastest possible speed permitted anywhere within our universe. This means that the sunlight currently warming Earth's surface at this very moment did not originate from fusion reactions occurring within the sun's core just 8 minutes ago, the time light actually requires to travel the considerable distance separating the sun and Earth once it has fully escaped the star itself. Instead, the specific energy contained within today's sunlight was actually generated deep within the sun's core tens of thousands of years in the past, only now finally completing its extraordinarily long, slow journey outward through the dense, obstructed radiative zone before finally escaping into the open space beyond. Once a photon finally completes this long, slow journey through the radiative zone, it encounters a second, notably different layer known as the convective zone, extending from roughly 70% of the sun's total radius outward to its visible surface. Within this outer convective zone, energy no longer travels primarily through the same slow, repeated process of photon absorption and re-emission that characterized its journey through the deeper radiative zone. Instead, energy transport within this region occurs primarily through convection, a process considerably more familiar to us here on Earth, similar in basic principle to the way heated water circulates within a pot brought slowly to boil. Within this convective zone, hot plasma rises steadily upward from the boundary with the radiative zone below, gradually cooling as it approaches the sun's surface, before eventually sinking back downward to be reheated once again, in a continuous churning cycle of rising and falling plasma that efficiently carries the remaining energy the final distance toward the sun's visible surface. This convective process, while considerably faster than the slow, obstructed journey through the radiative zone below, still requires a meaningful period of time, generally estimated at several weeks to a few months, before energy finally reaches the sun's outer surface and prepares for its final, dramatically different stage of travel. It is only once a photon finally reaches the sun's outer surface, escaping entirely from the dense, obstructed plasma that characterized its long journey through both the radiative and convective zones, that it finally begins moving freely and directly outward into the open vacuum of space, unobstructed by any further absorption or re-emission. From this point onward, the photon's journey transforms entirely, traveling now at light's full, uninterrupted speed, crossing the roughly 150 million kilometers separating the sun and Earth in a mere 8 minutes, a journey almost instantaneous compared to the tens of thousands of years required to simply escape the sun's own dense interior. This remarkable contrast between an almost unimaginably slow journey measured in tens of thousands of years within the sun itself, followed by a nearly instantaneous 8-minute journey across the vast emptiness of space, offers a genuinely humbling perspective on the true nature of sunlight. Every beam of sunlight warming your skin, every photon captured by a plant during photosynthesis, every particle of light detected by a telescope studying the sun from Earth, represents energy that began its existence deep within the sun's core tens of thousands of years ago, patiently working its way outward through dense, obstructed plasma across a span of time considerably longer than the entire recorded history of human civilization, before finally escaping and completing the remainder of its journey to Earth in the brief span of a single 8-minute afternoon. This extraordinarily long internal journey also helps explain another important characteristic of the sun's overall behavior, namely its remarkable stability and consistency as observed from Earth. Because energy generated through fusion within the core requires such an enormous span of time to work its way outward through the radiative and convective zones before finally reaching the surface. Any sudden, dramatic changes occurring deep within the sun's core would not become immediately visible at the surface, but would instead take tens of thousands of years to gradually propagate outward and become detectable, effectively smoothing out and stabilizing the sun's outward appearance despite whatever more dramatic changes might be occurring, largely unnoticed, deep within its hidden interior. Having finally traced this long, patient journey from the sun's core outward to its visible surface, we arrive now at the region most people instinctively imagine when picturing the sun itself, the bright, golden surface visible from Earth. Yet this seemingly familiar surface holds surprises of its own, revealing itself, upon closer examination, to be considerably less solid and considerably more dynamic than its calm, steady appearance from such a great distance might initially suggest. When we look up at the sun, however briefly and however carefully filtered that observation must be for safety, we see what appears to be a smooth, uniformly bright surface, a clearly defined edge separating the glowing star from the darkness of space surrounding it. Yet this apparent surface, the region scientists call the photosphere, is fundamentally different from any surface we might encounter here on Earth, possessing no solid form whatsoever, and instead representing something considerably more subtle and, in its own way, more remarkable. The photosphere is best understood not as a genuine physical surface, in the sense of a boundary between solid ground and open air, but rather as the specific layer within the sun's outer atmosphere where the surrounding plasma finally becomes transparent enough for light to escape freely into space. Below this layer, the sun's plasma remains so dense that light cannot travel far before being absorbed and re-emitted, exactly as we explored throughout the sun's long internal journey outward from its core. Above this layer, plasma density drops off considerably, allowing light to finally travel freely and directly outward, uninterrupted, toward Earth and the rest of the solar system. The photosphere then represents not a solid boundary, but rather the precise point at which the sun's plasma transitions from opaque to transparent, the effective edge of visibility rather than any genuine physical surface. Despite lacking any true solid form, the photosphere still possesses a definite measurable temperature, averaging approximately 5,500 degrees Celsius, a temperature far exceeding anything encountered under ordinary circumstances here on Earth, yet notably cooler than the sun's core, a temperature difference reflecting the tremendous energy loss that naturally occurs as heat gradually works its way outward across the considerable distance separating the core from the visible surface. Examined closely, particularly through specialized telescopes capable of resolving fine surface detail, the photosphere reveals itself to be considerably more dynamic and textured than its smooth, uniform appearance from a great distance might initially suggest. Rather than a calm, unbroken expanse, the photosphere displays a distinctive, ever-changing pattern known as granulation, a constantly shifting mosaic of individual cells, each typically spanning roughly 1,000 kilometers across, representing the visible tops of rising columns of hot plasma reaching the surface from the convective zone immediately below. The same convective process we explored in the previous chapter regarding energy's long journey outward from the sun's core. Each individual granule within this pattern typically persists for only a matter of minutes before dissipating and being replaced by a new granule forming nearby. A continuous, restless process of rising, cooling, and sinking plasma that gives the sun's surface its distinctive, ever-shifting texture when observed in sufficient detail. This granulation pattern offers direct, visible evidence of the ongoing convective processes occurring just beneath the surface, a visual signature of the same rising and sinking plasma responsible for carrying the final portion of the sun's energy outward toward its visible surface. Alongside this constant, subtle granulation pattern, the photosphere also periodically displays considerably larger, more distinctive features known as sunspots, darker regions appearing temporarily across portions of the sun's surface, sometimes growing large enough to be visible even through simple, properly filtered telescopes here on Earth. These sunspots appear notably darker than the surrounding photosphere not because they represent any absence of heat or energy, but rather because they are somewhat cooler than their immediate surroundings, typically registering temperatures several thousand degrees lower than the surrounding unaffected photosphere, a difference significant enough to make them appear visibly darker by comparison, despite still remaining, by any ordinary standard, extraordinarily hot. The underlying cause of these sunspots lies not within the photosphere itself, but rather within the sun's powerful and complex magnetic field, a topic we will explore in considerably greater detail throughout later chapters of this documentary. Sunspots form in regions where the sun's magnetic field becomes unusually concentrated and intense, effectively suppressing the normal convective transport of heat from below, resulting in a temporarily cooler, and therefore visibly darker, patch of photosphere at the location where this concentrated magnetic activity occurs. Sunspots do not appear randomly or continuously throughout the sun's history, but instead follow a broader, cyclical pattern that scientists have carefully tracked and documented across centuries of careful observation. The overall number of visible sunspots rises and falls according to an approximately 11-year cycle, gradually increasing from a period of relatively low activity, known as solar minimum, toward a period of considerably increased activity, known as solar maximum, before gradually declining once again toward the next minimum, in a continuous, repeating pattern that reflects broader cyclical changes occurring within the sun's overall magnetic behavior. A topic we will return to in greater depth later in this documentary when we explore solar storms and the sun's broader magnetic cycle. Beyond granulation and sunspots, careful observation of the photosphere has also revealed another genuinely fascinating characteristic of the sun's behavior, namely that it does not rotate as a single, uniform, solid object in the same way a rocky planet like Earth or Mars does. Instead, because the sun consists entirely of plasma rather than solid material, different regions of its surface are able to rotate at different rates, a phenomenon scientists call differential rotation. Specifically, the sun's equatorial regions complete a full rotation in approximately 25 days, while regions closer to its poles rotate considerably more slowly, requiring closer to 35 days to complete a single full rotation. This uneven differential rotation pattern would be entirely impossible for a solid, rigid body, and represents direct, visible evidence of the sun's fundamentally fluid, plasma-based composition, a composition that behaves according to considerably different physical rules than the solid, rocky surfaces we are more familiar with here on Earth and across the other rocky planets we have explored throughout this channel's documentary series. This differential rotation carries significant consequences extending well beyond simply the sun's own physical behavior, playing a crucial role in generating and continuously reshaping the sun's powerful magnetic field, a process that ultimately drives not only the sunspots we have explored throughout this chapter, but also the far more dramatic and occasionally violent solar storms we will examine in the chapters ahead, phenomena capable of extending their influence far beyond the sun itself, reaching outward across the solar system to affect Earth and every other planet within reach of the sun's considerable influence. Having explored the sun's dynamic, ever-shifting visible surface, we now turn our attention outward, beyond the photosphere entirely, into the sun's surrounding atmosphere, a region that holds one of the most persistent and genuinely puzzling mysteries in all of modern astrophysics. Beyond the photosphere, the layer we typically think of as the sun's visible surface, lies an extended, largely invisible atmosphere, one that remains hidden from ordinary observation, yet reveals itself to be even more dynamic and considerably more mysterious than the churning, granulated surface we explored in the previous chapter. Immediately above the photosphere lies a relatively thin layer known as the chromosphere, a region extending outward for only a few thousand kilometers, yet displaying temperatures that begin to rise once again after the relatively cooler conditions found at the photosphere itself. This reddish-hued layer, ordinarily far too faint to observe against the overwhelming brightness of the photosphere below, becomes briefly visible under one very specific set of circumstances, during the fleeting moments of a total solar eclipse, when the moon passes directly between Earth and the sun, precisely blocking the intensely bright photosphere while allowing the comparatively fainter chromosphere to become visible along the sun's edge, appearing briefly as a delicate reddish glow surrounding the darkened lunar silhouette. Beyond the chromosphere lies the sun's outermost atmospheric layer, known as the corona, an enormous, wispy region of extremely hot, diffuse plasma extending outward for millions of kilometers, far beyond the sun's visible surface, gradually thinning until it merges seamlessly into the solar wind, a topic we will explore in considerably greater detail in the following chapter. Like the chromosphere immediately below it, the corona remains ordinarily invisible to observers on Earth, its faint glow completely overwhelmed by the far brighter photosphere, except during those same brief, precious moments of a total solar eclipse, when the corona becomes visible as a delicate, sweeping halo of pale light extending outward from the darkened sun, one of the most visually striking natural phenomena observable anywhere on Earth. It is within this outer corona that scientists encounter one of the most persistent and genuinely puzzling mysteries in the entire field of solar physics, a mystery that has occupied researchers for decades without a complete, universally agreed-upon resolution. Given everything we have explored throughout this documentary regarding how energy travels outward from the sun's core, one would reasonably expect temperatures to decline steadily and predictably with increasing distance from that core, growing progressively cooler as we move outward through the radiative zone, the convective zone, and finally the visible photosphere itself. And indeed, this expected pattern holds true right up until we reach the corona. The photosphere, as we explored in the previous chapter, maintains an average temperature of roughly 5,500 degrees Celsius. Yet the corona, positioned considerably farther from the sun's core and separated from it by the cooler photosphere and chromosphere in between, somehow reaches temperatures of well over 1 million degrees Celsius, occasionally spiking even higher, a genuinely bewildering reversal of the pattern we would ordinarily expect based on simple distance from the sun's central energy source. This puzzle, known within the scientific community as the coronal heating problem, remains one of the most actively studied open questions in modern solar physics, a mystery we will return to in greater depth later in this documentary when we more broadly examine the sun's remaining unsolved scientific puzzles. For now, it is enough to appreciate the sheer strangeness of this reversal, a layer of the sun's atmosphere positioned farther from its core, yet somehow burning hundreds of times hotter than the visible surface positioned closer to that same central source of energy. While the precise mechanism responsible for this extreme coronal heating remains genuinely uncertain, current scientific understanding points strongly toward the sun's powerful and complex magnetic field as playing a central role, the same magnetic field responsible for the sunspots we explored in the previous chapter. Throughout the corona, this magnetic field frequently organizes itself into distinctive arching structures known as coronal loops, enormous, glowing arcs of plasma that trace the underlying magnetic field lines as they extend outward from the sun's surface, sometimes stretching hundreds of thousands of kilometers into space before curving back down and reconnecting with the surface at another location. These coronal loops offer scientists a rare, directly visible glimpse of the sun's otherwise invisible magnetic field structure, their glowing plasma essentially tracing an outline of magnetic field lines that would otherwise remain entirely undetectable through ordinary visual observation. Many current theories regarding the coronal heating problem suggest that these magnetic field lines, twisted and tangled by the sun's differential rotation that we explored in the previous chapter, may periodically release tremendous bursts of energy as they snap, reconnect, and reorganize themselves, a process that could potentially account for at least a significant portion of the corona's otherwise mysterious extreme heat, injecting sudden, concentrated bursts of energy directly into the surrounding plasma through this ongoing process of magnetic tension and release. Beyond its role in this unsolved heating mystery, the corona also holds particular significance as the specific region from which the solar wind, a continuous outward stream of charged particles that we will explore in considerable detail in the following chapter, ultimately originates. The corona's extreme temperature, however mysterious its precise cause remains, provides charged particles with more than enough energy to escape the sun's gravitational pull entirely, streaming outward across the solar system and eventually interacting with every planet positioned within reach of the sun's considerable influence, Earth very much included. Total solar eclipses, those brief, precious moments when the moon's precise alignment allows both the chromosphere and corona to become directly visible from Earth's surface, have historically provided scientists with invaluable opportunities to study these otherwise hidden atmospheric layers in considerable detail. Long before modern spacecraft made it possible to study the sun's atmosphere through specialized instruments capable of blocking the photosphere's overwhelming brightness artificially, astronomers relied almost entirely on these rare, fleeting eclipse events to gather any meaningful data regarding the sun's extended atmosphere, carefully preparing specialized equipment and traveling considerable distances to position themselves precisely within the narrow path where a given eclipse would become total, rather than merely partial. Today, dedicated spacecraft equipped with instruments called coronagraphs, specifically designed to artificially block the photosphere's overwhelming light in a manner similar to the moon's natural blocking effect during a genuine eclipse, allow scientists to study the corona continuously, without needing to wait for the relatively rare natural alignment of a genuine solar eclipse. This ongoing capability has proven invaluable for monitoring the corona's behavior in real time, particularly regarding the dramatic, occasionally violent eruptions that can occur within this outer atmospheric layer, eruptions capable of sending powerful bursts of charged particles hurtling outward across the solar system, carrying potentially significant consequences for Earth and the technology increasingly woven throughout modern human civilization. Yet even after decades of dedicated study, both through natural eclipse observation and continuous spacecraft monitoring, the corona continues to guard many of its deepest secrets closely, its extreme, still not fully explained heat serving as a persistent reminder that even after centuries of careful observation, the star at the center of our own solar system remains, in many genuine and significant ways, only partially understood. Beneath the corona's mysterious, superheated glow, and closely tied to the same tangled magnetic field lines responsible for the coronal loops we explored in the previous chapter, the sun periodically unleashes some of the most powerful and genuinely violent events found anywhere within our solar system. Sudden, dramatic releases of energy capable of reshaping conditions not only near the sun itself, but across vast distances, reaching outward to directly affect Earth and the technology increasingly essential to modern human civilization. The first and generally less dramatic of these two related phenomena is known as a solar flare, a sudden, intense burst of radiation released from the sun's surface, typically originating from the same active regions where sunspots and their associated tangled magnetic fields tend to concentrate. Solar flares occur when the sun's magnetic field lines, twisted and stressed by the differential rotation we explored several chapters ago, suddenly snap and reconnect in a process scientists call magnetic reconnection, releasing a tremendous burst of stored magnetic energy in the process, energy that radiates outward primarily in the form of intense radiation spanning across a considerable range of wavelengths, including significant bursts of X-ray and ultraviolet radiation. This process of magnetic reconnection can be understood in simplified terms as somewhat similar to twisting a rubber band with increasing tension until it suddenly snaps, releasing all of its accumulated stress in a single, sudden burst. Within the sun's magnetic field, this same basic principle applies on an almost unimaginably larger scale, with twisted, stressed magnetic field lines suddenly reorganizing themselves into a simpler, lower energy configuration, releasing the difference in energy outward in the form of an intense, sudden flare, an event that can unfold within a matter of minutes, yet release energy equivalent to millions of the most powerful nuclear weapons ever created, detonated simultaneously. Solar flares are frequently, though not always, accompanied by an even more dramatic and consequential phenomenon, one known as a coronal mass ejection, or CME. where a solar flare primarily releases energy in the form of intense radiation. A coronal mass ejection involves the actual physical ejection of an enormous quantity of solar plasma and magnetic field material, hurled outward from the corona into space at tremendous speed, sometimes exceeding several million kilometers per hour, depending on the specific intensity of the underlying eruption responsible for launching this material outward. Unlike the radiation released during a solar flare, which travels outward at the speed of light and reaches Earth in roughly 8 minutes, the physical plasma ejected during a coronal mass ejection travels considerably slower, though still at tremendous speed by any ordinary standard, typically requiring anywhere from 1 to several days to complete the journey from the Sun to Earth, depending on the specific speed and trajectory of the individual eruption involved. Together, solar flares and coronal mass ejections represent the primary components of what scientists collectively refer to as space weather, a broader term describing the constantly changing conditions within the solar system driven by the Sun's variable activity, conditions capable of meaningfully affecting not only the space immediately surrounding Earth, but occasionally reaching down to influence conditions on Earth's own surface as well, particularly regarding sensitive electronic and technological systems. When a sufficiently powerful coronal mass ejection reaches Earth, its enormous cloud of charged particles interacts directly with Earth's own magnetic field, a topic we will explore in considerably greater detail in the following chapter regarding the broader solar wind. This interaction can trigger a range of consequences, from the relatively benign and genuinely beautiful to the potentially serious and technologically disruptive, depending on the specific strength of the individual event involved. Among the most visually spectacular consequences of this interaction is the aurora, the shimmering, colorful displays of light visible near Earth's polar regions, sometimes extending to considerably lower latitudes during particularly powerful events. These auroral displays occur when charged particles from the Sun, channeled by Earth's magnetic field toward the polar regions, collide with molecules within Earth's upper atmosphere, exciting these atmospheric molecules and causing them to emit visible light in the process. Similar in basic principle to the way a fluorescent light bulb generates its own glow through excited gas molecules, though occurring here on a vastly grander, entirely natural scale, painting the night sky with sweeping curtains of green, red, and occasionally purple light. While auroras themselves represent a genuinely beautiful, harmless consequence of the Sun's activity, sufficiently powerful coronal mass ejections can also generate considerably more serious, disruptive effects, particularly regarding modern technological infrastructure. The same charged particles responsible for generating auroral displays can also induce powerful electrical currents within long conductive systems here on Earth, including power grids, pipelines, and other extended electrical infrastructure, occasionally causing significant disruptions or even physical damage to sensitive equipment when a particularly powerful event occurs. Perhaps the most famous historical example of this kind of disruptive space weather event occurred in 1859, an event now known as the Carrington Event, named after the British astronomer who carefully documented the associated solar flare at the time. This exceptionally powerful coronal mass ejection generated auroral displays visible at unusually low latitudes across the globe, while simultaneously inducing powerful electrical currents strong enough to disrupt telegraph systems across Europe and North America, the primary long-distance electrical communication technology available during that particular period of history. Given humanity's considerably greater current dependence on sensitive electronic and satellite-based technology compared to the relatively simple telegraph systems affected during the Carrington Event, scientists continue to closely monitor the Sun's activity, watching carefully for signs of similarly powerful eruptions that could potentially cause significantly more serious disruption to modern power grids, satellite communication systems, and other essential technological infrastructure increasingly woven throughout nearly every aspect of contemporary human civilization. This ongoing need for careful monitoring highlights an important, broader theme that continues to emerge throughout this documentary: the recognition that the Sun, despite its calm, steady appearance from the safety of Earth's surface, remains a genuinely dynamic, occasionally volatile star, capable of unleashing tremendous bursts of energy that, while originating some 150 million kilometers away, remain fully capable of reaching across that enormous distance to meaningfully affect conditions here on Earth. Beyond the dramatic, episodic violence of solar flares and coronal mass ejections that we explored in the previous chapter, the Sun also generates a far more constant, continuous form of outward influence, one that never truly stops, streaming outward in every direction, across every moment of the Sun's existence. This is the solar wind, a steady, ongoing flow of charged particles, primarily electrons and protons, continuously escaping the Sun's corona and streaming outward across the entire solar system. Unlike the sudden, dramatic bursts associated with solar flares and coronal mass ejections, the solar wind represents a persistent, background phenomenon present at every single moment, its intensity varying somewhat according to the Sun's broader activity cycle, yet never fully ceasing entirely. This continuous outward flow originates directly from the corona, the same extraordinarily hot, mysterious outer atmospheric layer we explored in detail 2 chapters ago, where temperatures reach sufficiently extreme levels to provide charged particles with more than enough energy to overcome the Sun's considerable gravitational pull and escape outward into space entirely. As these charged particles stream outward from the Sun, they gradually fill an enormous, bubble-like region of space surrounding our entire solar system, a region scientists call the heliosphere. This vast bubble, inflated continuously by the Sun's ongoing solar wind, extends far beyond the orbit of Neptune, the outermost planet we explored in considerable detail throughout an earlier documentary, encompassing the entire solar system, and continuing to expand outward until it eventually encounters sufficient resistance from the surrounding interstellar medium, the extremely thin, diffuse material that fills the vast spaces between individual star systems throughout our galaxy. The heliosphere serves a genuinely significant protective function for every planet positioned within its boundaries, including Earth, helping to shield the entire solar system from a portion of the potentially harmful cosmic radiation that continuously streams inward from beyond, generated by distant supernovae and other energetic events occurring throughout the broader galaxy. In this sense, the Sun's own solar wind, while occasionally posing certain challenges regarding space weather here on Earth, as we explored in the previous chapter, simultaneously provides a broader protective benefit, helping to shield our entire solar system from an even more intense, unfiltered stream of cosmic radiation that would otherwise penetrate considerably deeper into our planetary neighborhood. For Earth specifically, an additional, more localized layer of protection exists as well, one we have referenced briefly throughout our previous documentary regarding Mars, and one worth exploring here in somewhat greater detail, given its direct connection to the Sun's continuous solar wind. Earth possesses its own global magnetic field, generated deep within its molten outer core, extending outward into space and forming a protective magnetic bubble, sometimes called the magnetosphere, that deflects the vast majority of incoming solar wind particles safely around our planet, rather than allowing them to interact directly with our atmosphere. This protective magnetosphere represents an essential factor in maintaining Earth's long-term habitability, precisely the same essential factor whose absence, as we explored extensively throughout our Mars documentary, allowed the solar wind to gradually strip away Mars's own once thicker atmosphere across billions of years, following the collapse of that planet's own protective magnetic field early in its history. Earth's continued possession of this same protective magnetic shield stands as one of the fundamental reasons our planet has retained its thick, life-sustaining atmosphere across the same enormous span of time that saw Mars's own atmosphere gradually eroded away into the surrounding vacuum of space. Not every planet within our solar system benefits from this same kind of magnetic protection, and the resulting differences offer scientists valuable insight into how the solar wind interacts differently across a range of planetary environments. Venus, despite being similar in overall size to Earth, lacks any significant global magnetic field of its own, yet has managed to retain an extraordinarily thick atmosphere regardless, primarily due to its considerably stronger gravitational pull compared to Mars, along with other complex atmospheric factors that continue to be studied and refined by planetary scientists. Mercury, positioned considerably closer to the Sun and therefore exposed to a significantly more intense solar wind, does possess a modest magnetic field of its own, though one considerably weaker than Earth's, offering correspondingly less complete protection against the intense solar wind present so close to its source. Beyond its interaction with individual planets throughout the inner solar system, the solar wind's influence extends dramatically outward across the entire heliosphere, eventually reaching a boundary region where its outward pressure finally weakens sufficiently to be overcome by the surrounding interstellar medium, the thin, diffuse material filling the vast spaces between our solar system and its neighboring star systems throughout the galaxy. This boundary, marking the practical edge of the Sun's direct influence, represents one of the most significant thresholds within our entire solar system, the genuine transition point between our own local solar environment and the broader galactic environment beyond. Remarkably, humanity has actually sent a spacecraft far enough to directly cross this significant boundary, providing invaluable direct measurements of this otherwise entirely theoretical transition zone. Voyager 1, launched in 1977 and already familiar to us from our earlier discussion of its twin spacecraft's historic flyby of Neptune, continued traveling outward long after completing its own primary mission studying the outer planets, eventually crossing into interstellar space in 2012, becoming the first human-made object to travel beyond the heliosphere entirely, directly confirming through its own onboard instruments. The dramatic transition from the Sun's own local solar wind to the considerably different conditions found within the broader interstellar medium beyond. This remarkable achievement offers a fitting, tangible confirmation of just how vast the Sun's continuous influence truly extends, a bubble of solar wind stretching for many billions of kilometers beyond even the most distant planets within our solar system, shaping and protecting the entire region we call home, before finally yielding to the broader, considerably more mysterious galactic environment extending far beyond. Having now explored the Sun's continuous outward influence extending across the entire solar system, we turn next to examine more specifically how this same solar wind, along with the Sun's broader light and gravitational influence, has shaped and continues to shape every individual planet within our solar system, from small, scorched Mercury orbiting closest to the Sun's intense heat, to distant, windswept Neptune marking the very edge of our planetary neighborhood. Having traced the Sun's energy from its birth deep within the core, through its long journey outward to the surface, and finally across the vast reaches of the heliosphere itself, we now turn our attention outward toward the family of planets that owe their very existence, their orbits, their climates, and in many cases their entire histories, to this single, dominant star at the center of our solar system. Mercury, the innermost planet, experiences the Sun's influence more directly and more intensely than any other world in our solar system. Orbiting at less than half the distance separating Earth from the Sun, Mercury receives solar radiation more than 6 times more intense than what reaches Earth's surface, subjecting its daytime hemisphere to temperatures exceeding 400 degrees Celsius. Yet Mercury's extraordinarily thin atmosphere, offering almost no meaningful insulation, allows this same planet to plunge to temperatures below -170 degrees Celsius during its long nights, producing the most extreme temperature swings found anywhere in our solar system, a direct and unfiltered consequence of Mercury's close proximity to the Sun's intense energy output, combined with its near-total inability to retain any of that heat once darkness falls. Venus, though positioned considerably farther from the Sun than Mercury, presents an even more extreme example of solar influence, though through an entirely different mechanism. Rather than experiencing Mercury's dramatic swings between scorching days and freezing nights, Venus maintains a remarkably consistent surface temperature exceeding 460 degrees Celsius, hot enough to melt lead, regardless of whether a given location happens to be facing toward or away from the sun at any particular moment. This consistent extreme heat results not directly from Venus's distance from the sun, but rather from its extraordinarily thick atmosphere, composed primarily of carbon dioxide, which traps incoming solar energy through an intense greenhouse effect, a dramatic runaway version of the same basic atmospheric warming process that, in a far more moderate and carefully balanced form, helps maintain Earth's own comfortable, life-sustaining temperatures. Earth itself, positioned at what scientists often call the right distance within our sun's habitable zone, receives solar energy in a quantity and at an intensity precisely suited to maintaining stable liquid water across significant portions of its surface, the essential ingredient that has allowed life to emerge, evolve, and flourish across billions of years of relatively stable climate conditions. This delicate balance depends not only on Earth's specific distance from the sun, but also on our planet's atmospheric composition, its protective magnetic field that we explored in the previous chapter, and numerous other interconnected factors that together have allowed Earth to maintain conditions favorable for life across an almost unimaginably long span of geological time. Mars, as we explored in extensive detail throughout our previous documentary, once likely benefited from a considerably warmer climate during its own early history, sustained partly by a thicker atmosphere capable of trapping more of the sun's incoming energy through greenhouse warming. Yet Mars's eventual loss of its own protective magnetic field and the subsequent erosion of its atmosphere by the continuous solar wind we examined in the previous chapter gradually transformed this once warmer, wetter world into the cold, thin-atmosphered desert we observe today, a transformation driven directly by the same fundamental solar processes we have explored throughout this documentary, interacting differently with Mars's own particular characteristics compared to Earth's. Beyond Mars, the solar system's four gas giants, Jupiter, Saturn, Uranus, and Neptune, orbit at such considerable distances from the sun that direct solar heating plays a considerably smaller role in shaping their overall character compared to the rocky, inner planets we have just explored. Jupiter, despite orbiting at more than 5 times Earth's distance from the sun, still experiences meaningful solar influence, particularly regarding its interaction with the solar wind, which helps generate Jupiter's own powerful auroral displays, similar in basic principle to Earth's own aurora, though considerably more intense given Jupiter's exceptionally powerful magnetic field, the strongest possessed by any planet within our solar system. Saturn, positioned nearly twice as far from the sun as Jupiter, receives correspondingly less direct solar heating, yet still experiences meaningful seasonal variation across its own lengthy, nearly 30-year orbit, driven by the same basic axial tilt responsible for Earth's own familiar seasons, though unfolding across a considerably longer timescale given Saturn's much greater orbital period. Neptune, the subject of our very first documentary in this series, orbits at such an extraordinary distance from the sun, nearly 30 times farther than Earth itself, that it receives only a tiny fraction of the solar energy reaching our own planet, roughly 900 times less intense than the sunlight we experience here on Earth. And yet, as we explored extensively throughout that earlier documentary, Neptune somehow generates the fastest sustained winds found anywhere in our solar system, a genuine puzzle given how little direct solar energy actually reaches this distant, windswept world, a mystery that continues to point toward Neptune's own significant internal heat source as the primary driver of its extraordinary atmospheric behavior, rather than any direct influence from the distant, faint sun. Even Pluto, no longer classified as a full planet but still an object of considerable scientific interest, orbits at such an extreme distance from the sun, on average more than 39 times farther than Earth, that sunlight reaching its frozen surface arrives with barely any meaningful warmth at all, appearing from Pluto's own surface as little more than an unusually bright star, rather than the clearly defined, warming disk we experience here on Earth. Despite this extraordinary distance and correspondingly minimal direct solar heating, Pluto still experiences subtle seasonal variations across its own lengthy 248-year orbit, driven by slight changes in its distance from the sun and its own particular axial tilt, demonstrating that even at the most extreme distances within our solar system, the sun's influence, however faint, continues to shape conditions across every world orbiting within its reach. Considered together, this survey across our entire solar system reveals a consistent, underlying truth that has run throughout this documentary from its earliest chapters. Every planet, from scorched Mercury to distant, frozen Pluto, exists in its own particular form entirely because of its specific relationship with the Sun. Whether shaped through direct heating, atmospheric interaction, magnetic field behavior, or the continuous influence of the solar winds streaming outward across the entire heliosphere. The Sun does not merely illuminate our solar system from a distance. It actively shapes and continues to shape the fundamental character of every single world orbiting within its gravitational influence, a silent, constant force whose effects we have now traced across the full breadth of our solar system, from its innermost, scorched world to its most distant, frozen edges. Having explored the Sun's influence across our entire family of planets, we now turn our attention back toward Earth itself, and toward the long, gradually evolving relationship between humanity and the star that has shaped our own planet's history, since long before anyone possessed the scientific understanding necessary to fully appreciate what the Sun truly represents. Long before telescopes revealed the Sun's true nature as a distant, nuclear-powered star, and long before any scientific understanding of fusion, plasma, or magnetic fields existed, humanity's relationship with the Sun was built entirely through careful observation, deep reverence, and a growing understanding of its essential role in sustaining daily life. This relationship, stretching back across the entire span of human civilization, offers its own quiet, fascinating story, one that gradually transformed the Sun from an object of worship into a subject of rigorous scientific study. Among the earliest and most elaborate civilizations to develop a sophisticated relationship with the Sun were the ancient Egyptians, who placed solar worship at the very center of their religious and cultural life. The Egyptian sun god Ra was regarded as one of the most powerful and important deities within their entire pantheon, believed to travel across the sky each day in a solar barge, before journeying through the underworld each night, only to be reborn again with each new sunrise. This daily cycle of the sun's apparent movement across the sky became deeply woven into Egyptian concepts of death, rebirth, and the fundamental order of the universe itself, reflected clearly in monuments like the Great Pyramids, many of which were carefully aligned with specific solar events, demonstrating a sophisticated practical understanding of the sun's predictable movements, even without any genuine scientific comprehension of what the sun actually was. Ancient Greek civilization approached the sun somewhat differently, gradually shifting from purely mythological explanations toward increasingly systematic, observational astronomy. While early Greek mythology similarly personified the sun as a god, Helios, driving a fiery chariot across the sky each day, later Greek astronomers and philosophers began developing more rigorous, mathematically grounded models, attempting to explain the sun's observed movements and its broader relationship to Earth and the other visible planets. Figures like Aristarchus of Samos proposed remarkably early versions of a heliocentric model, correctly suggesting that Earth orbited the sun rather than the reverse, an idea that, despite its accuracy, would not become widely accepted for many centuries to come, largely overshadowed by the more intuitively appealing, though ultimately incorrect, geocentric model that placed Earth at the center of the universe. This geocentric view, further developed and formalized by later astronomers including Ptolemy, remained the dominant scientific understanding for well over 1,000 years, deeply influencing both Western and Islamic astronomical thought throughout much of this extended period. It was not until the 16th century that this long-standing model finally began to be seriously challenged, initially through the work of Nicolaus Copernicus, who revived and further developed the heliocentric model first proposed by Aristarchus many centuries earlier, correctly placing the sun, rather than Earth, at the center of our solar system. This revolutionary shift toward a genuinely accurate understanding of the sun's central role within our solar system gained considerable additional support through the work of Galileo Galilei in the early 17th century. Using one of the first telescopes ever applied to serious astronomical observation, Galileo made a series of groundbreaking discoveries that provided compelling, direct observational evidence supporting the heliocentric model, including his careful documentation of sunspots, the same dynamic surface features we explored in detail several chapters ago. Galileo's careful tracking of these sunspots as they moved gradually across the sun's visible surface provided crucial evidence supporting the sun's own rotation, directly contradicting the older, geocentric assumption that the sun and stars existed as fixed, unchanging bodies revolving passively around a stationary Earth. Galileo's telescopic observations of the sun, conducted well before any adequate understanding existed regarding the serious risks of direct solar observation, notably contributed to the gradual deterioration of his own eyesight later in life, a sobering historical reminder of the genuine dangers involved in observing the sun directly, dangers that remain just as significant today, and that continue to require careful, specialized equipment and filtering techniques for any safe. Direct solar observation, whether through a telescope or the unaided human eye. Following Galileo's foundational contributions, astronomical understanding of the sun continued advancing steadily across subsequent centuries, gradually incorporating increasingly sophisticated scientific tools and theoretical frameworks. The development of spectroscopy during the 19th century, a technique allowing scientists to analyze the specific wavelengths of light emitted by the sun, proved particularly transformative, eventually enabling researchers to determine the sun's precise chemical composition from a distance of 150 million kilometers, revealing hydrogen and helium as its overwhelmingly dominant constituent elements. Long before any direct scientific understanding existed regarding the specific nuclear fusion process occurring deep within the sun's core. The eventual scientific understanding of nuclear fusion itself, the process we explored in considerable detail several chapters ago as the true source of the sun's tremendous energy output, did not emerge until the 20th century, drawing upon significant advances in nuclear physics that had only recently become possible through humanity's growing understanding of atomic structure and behavior. This relatively recent scientific breakthrough, arriving only within the past century, finally provided a complete, physically grounded explanation for a question that had genuinely puzzled scientists for generations, namely how the sun could possibly continue generating such tremendous energy output continuously across a timespan clearly measured in billions of years, a question that earlier scientific frameworks, however sophisticated for their particular era, had simply been unable to adequately answer. The invention and gradual refinement of modern telescopes, extending well beyond Galileo's own early, relatively simple instrument, has continued dramatically expanding humanity's capacity to study the sun in ever-increasing detail. Specialized solar telescopes, equipped with sophisticated filtering technology, designed to safely block the vast majority of incoming solar radiation while still permitting detailed observation of specific features, have allowed astronomers to study sunspots, granulation, and other surface phenomena with remarkable precision, building steadily upon the foundational observations Galileo first documented centuries earlier using considerably more limited technology. This long historical arc, stretching from ancient Egyptian solar worship through Greek philosophical speculation, Copernican revolution, Galilean telescopic observation, and eventually toward a complete, scientifically grounded understanding of nuclear fusion itself, reflects a broader pattern we have now encountered repeatedly throughout this documentary series. Humanity's understanding of the natural world tends to develop gradually, incrementally, each generation building carefully upon the observations and insights of those who came before, slowly transforming ancient reverence and mythology into increasingly precise, evidence-based scientific understanding, a transformation that, in the case of the sun specifically, has only truly accelerated within the most recent century of this otherwise multi-thousand-year story. Yet even this remarkable scientific progress, spanning millennia of careful human observation and centuries of increasingly sophisticated telescopic study, remained fundamentally limited by one persistent, unavoidable constraint, namely the enormous physical distance separating Earth from the Sun itself. A distance that, until relatively recently, made any form of direct, close-up study entirely impossible, restricting humanity to studying the Sun exclusively from the safety and considerable remove of Earth's own surface. For nearly the entire span of human history, our understanding of the Sun depended entirely on observation from a single, fixed vantage point, Earth's own surface, separated from the Sun itself by roughly 150 million kilometers of open space. This changed dramatically over the past several decades, as humanity finally developed the technological capability to send dedicated spacecraft directly toward the Sun, gathering data far more detailed and considerably closer than anything achievable through even the most sophisticated Earth-based telescope. Among the earliest and most significant of these dedicated solar missions was SOHO, the Solar and Heliospheric Observatory, a joint mission between NASA and the European Space Agency launched in 1995. Rather than traveling directly toward the Sun itself, SOHO was positioned at a specific gravitational balance point between Earth and the Sun, a location allowing it to maintain a continuous, uninterrupted view of our star while remaining relatively close to Earth for purposes of ongoing communication and data transmission. Over the many years since its launch, SOHO has provided invaluable, continuous monitoring of the Sun's activity, including detailed observations of coronal mass ejections as they first begin forming, along with extensive data regarding the Sun's broader magnetic behavior and its complex, ongoing activity cycle, insights that have proven essential for understanding the space weather phenomena we explored in earlier chapters of this documentary. While SOHO provided invaluable long-term monitoring from a relatively safe, stable position, scientists increasingly recognized that fully understanding the Sun's most persistent mysteries, particularly the coronal heating problem we explored several chapters ago, would require spacecraft capable of traveling considerably closer to the Sun itself, directly sampling the extreme conditions found within the corona rather than observing them only from a considerable distance. This ambition, once considered technically impossible given the extraordinary heat and radiation involved, eventually became reality through NASA's Parker Solar Probe, launched in 2018 and named in honor of physicist Eugene Parker, who first theorized the existence of the solar wind decades before its eventual direct confirmation. The Parker Solar Probe represents one of the most technically remarkable spacecraft ever constructed, specifically engineered to survive conditions that would rapidly destroy virtually any other spacecraft ever built. Rather than attempting to travel directly toward the Sun in a single trajectory, the Parker Solar Probe instead follows a carefully designed series of increasingly close orbital passes, using repeated gravitational assists from Venus to gradually tighten its orbital path, drawing closer to the Sun with each successive pass across a mission spanning multiple years. To survive the extraordinary heat encountered during its closest approaches, the Parker Solar Probe relies on a specially engineered heat shield, constructed from advanced carbon composite materials capable of withstanding temperatures exceeding 1300 degrees Celsius, while simultaneously protecting the spacecraft's sensitive scientific instruments, positioned safely in the shield's shadow at a considerably more moderate operating temperature. During its closest orbital passes, the Parker Solar Probe travels directly through the Sun's corona itself, becoming the first spacecraft in history to physically enter this extraordinary outer atmospheric layer, gathering direct, in situ measurements of the exact conditions responsible for the coronal heating mystery we explored earlier in this documentary. These direct measurements have already provided scientists with considerable new insight regarding the corona's extreme temperatures and the underlying behavior of the solar wind. Though the coronal heating problem itself remains, even with this remarkable new data, not yet fully and completely resolved, a persistent reminder that even our closest, most direct scientific investigation of the Sun continues to reveal new layers of complexity alongside each new discovery. Complementing the Parker Solar Probe's extraordinarily close approach, the European Space Agency's Solar Orbiter, launched in 2020, takes a somewhat different but equally valuable approach towards studying the sun in unprecedented detail. Rather than prioritizing the closest possible physical approach, Solar Orbiter is specifically designed to capture detailed images and measurements of the sun's polar regions, areas that remain extremely difficult to observe clearly from Earth's own position within the flat, roughly equatorial plane of our solar system. By gradually adjusting its orbital inclination across multiple gravitational assists from Venus, Solar Orbiter has provided humanity's first genuinely detailed images of the sun's polar regions, offering valuable new insight into the sun's complex magnetic field structure, particularly regarding how this structure varies between the sun's equatorial and polar regions. Together, these complementary missions, SOHO's long-term continuous monitoring, the Parker Solar Probe's extraordinarily close, direct sampling of the corona itself, and Solar Orbiter's unique polar perspective, represent an unprecedented, coordinated scientific effort to finally understand the sun not merely as a distant source of light and warmth, but as a genuinely complex, dynamic astrophysical object worthy of the same detailed, direct scientific investigation, previously reserved primarily for the planets and other more physically accessible objects within our solar system. The data gathered through these missions has already meaningfully advanced scientific understanding across numerous areas we have explored throughout this documentary, providing considerably more detailed insight into the precise mechanisms driving solar flares and coronal mass ejections, refining our understanding of how the solar wind originates and accelerates outward from the corona, and offering valuable new data points that continue informing the ongoing, still not fully resolved investigation into the coronal heating problem itself. Beyond these currently active missions, scientists and mission planners continue developing additional concepts for future solar exploration, building upon the considerable technical achievements already demonstrated through Parker Solar Probe and Solar Orbiter. These future mission concepts generally aim to gather increasingly detailed, direct measurements of the sun's behavior, further refining our understanding of the remaining mysteries that continue to surround this star at the center of our solar system. Mysteries that, despite centuries of dedicated observation and now decades of direct spacecraft investigation, remain only partially resolved even today. This ongoing, active era of direct solar exploration represents a genuinely remarkable achievement, particularly when considered alongside the long historical arc we traced throughout the previous chapter, extending from ancient solar worship through Galileo's early telescopic observations, and now culminating in spacecraft capable of physically traveling directly through the sun's own corona, gathering data once considered entirely impossible to obtain. And yet, despite this remarkable technical achievement, a natural question inevitably arises regarding the fundamental limits of this kind of direct solar exploration, particularly regarding whether humanity might one day send not merely robotic spacecraft, but human beings themselves, close enough to genuinely and directly experience the sun's extraordinary environment firsthand. Having explored the remarkable technical achievement of spacecraft like the Parker Solar Probe, capable of traveling directly through the sun's own corona and surviving conditions once considered entirely beyond the reach of human engineering, a natural question follows from this achievement, one that captures the imagination in a way perhaps only the sun itself can inspire. Could human beings ever follow this same path, traveling close enough to genuinely experience the sun directly, rather than studying it only through the careful, remote instruments of robotic spacecraft? The honest, straightforward answer, grounded firmly in our current scientific and technological understanding, is no, and likely never will be, at least not in any manner resembling human presence anywhere close to the sun's actual surface or corona. The reasons behind this firm limitation become clear when we consider the sheer scale of the physical challenges involved. Challenges that make even the extraordinary achievement of the Parker Solar Probe, itself an entirely robotic and carefully engineered spacecraft, seem almost modest by comparison to what any human mission would require. Temperature represents perhaps the most immediately obvious barrier to any form of direct human approach toward the sun. As we explored in earlier chapters, the sun's visible surface, the photosphere, maintains an average temperature of roughly 5,500 degrees Celsius, while the corona surrounding it, despite its lower density, reaches temperatures exceeding 1 million degrees Celsius. Even the Parker Solar Probe, during its closest orbital passes, must rely on its specially engineered heat shield to protect its sensitive instruments from the intense heat encountered even at a considerable remaining distance from the sun's actual surface, a distance still measured in millions of kilometers, rather than any distance that could reasonably be described as physically close to the sun itself. No currently conceivable form of physical shielding or life support technology could plausibly protect a human being, or the considerably more complex biological and mechanical systems required to sustain human life, from temperatures anywhere close to those found within the sun's corona, let alone its visible surface. The engineering challenge extends well beyond simply blocking heat, given that any human spacecraft would also need to actively manage and dissipate this absorbed thermal energy, a problem that grows exponentially more difficult the closer any spacecraft, human-crewed or otherwise, attempts to travel toward the sun's overwhelming heat output. Beyond temperature alone, radiation presents an equally serious, and in some ways even more fundamentally challenging obstacle. As we explored in earlier chapters regarding solar flares and coronal mass ejections, the sun regularly releases intense bursts of radiation spanning a considerable range of wavelengths, including significant quantities of harmful X-ray and ultraviolet radiation. Even at Earth's considerable distance from the sun, this radiation requires careful management for astronauts operating in space, where they lack the protective benefit of Earth's thick atmosphere and magnetic field. Any human mission attempting to travel significantly closer to the sun would face radiation levels dramatically more intense than anything encountered even during current spacewalk operations or lunar missions. Levels that would likely prove lethal within a matter of minutes or even seconds, depending on the specific proximity involved, rather than posing merely an elevated long-term health risk of the kind we discussed regarding potential human settlement on Mars. Given these overwhelming combined challenges of extreme heat and intense radiation, scientists generally consider the closest safe approach for any human-crewed mission to remain vastly, almost incomparably farther from the sun than even the remarkably close distances achieved by robotic spacecraft like the Parker Solar Probe. Some theoretical mission concepts have considered human-crewed spacecraft potentially approaching to a distance somewhat closer than Mercury's own orbit, still tens of millions of kilometers from the sun's actual surface. Yet even this considerably more modest approach would require radiation shielding and thermal management technology considerably beyond anything currently available or realistically foreseeable within the near future. It is worth pausing to appreciate the genuine engineering achievement represented by the Parker Solar Probe specifically in this context, given that even this remarkable purpose-built robotic spacecraft, engineered with humanity's most advanced available heat-shielding technology, still maintains a considerable protective distance from the sun's actual visible surface during even its very closest orbital passes, a distance that, despite representing an extraordinary technical achievement by any reasonable standard, still amounts to millions of kilometers of remaining separation, a distance dwarfing anything that could reasonably be described as physically touching or directly experiencing the sun itself. This fundamental limitation reflects something genuinely important about the sun's true nature, one that stands in useful contrast to the other exploration challenges we have examined throughout this broader documentary series. Where human exploration of Mars, as we explored extensively throughout our previous documentary, presents formidable but potentially solvable engineering challenges, achievable given sufficient technological development across coming decades, direct human exploration anywhere close to the sun represents an entirely different category of challenge, one rooted not in currently unsolved engineering problems awaiting future technological breakthroughs, but rather in fundamental physical limitations that appear likely to remain permanently insurmountable, regardless of however far human technology may continue advancing across future centuries. This distinction offers a valuable, grounding perspective regarding the true nature of our relationship with the Sun, one that differs meaningfully from our relationship with the various planets we have explored throughout this broader documentary series. While humanity may indeed eventually establish a genuine, sustained presence on Mars, and continues actively working toward that ambitious goal, our relationship with the Sun itself will likely remain permanently limited to careful, remote observation and increasingly sophisticated robotic exploration, rather than any form of direct human presence anywhere close to the star's own overwhelming heat and radiation. In this sense, the Sun occupies a genuinely unique position within our broader exploration of the solar system, a star we can study with remarkable precision through increasingly advanced robotic spacecraft, yet one that will likely always remain fundamentally beyond humanity's own direct physical reach, a boundary defined not by any limitation of human ambition or ingenuity, but by the basic, unchanging physical reality of what the Sun actually is. An object of such overwhelming heat and energy that even our most remarkable engineering achievements can only ever approach it from a considerable, carefully calculated distance. Despite everything we have explored throughout this documentary, from the Sun's fusion-powered core to the spacecraft now flying directly through its corona, the star at the center of our solar system continues to guard a genuine collection of unresolved scientific puzzles, questions that persist even after centuries of careful observation and, more recently, decades of direct spacecraft investigation. We have already examined the coronal heating problem in some detail, that persistent puzzle regarding why the corona burns hundreds of times hotter than the surface positioned closer to the Sun's core. This remains, even today, formally unsolved, though missions like the Parker Solar Probe continue gathering data that scientists hope will eventually provide a complete answer. Rather than revisit that particular mystery, let us turn instead to several additional, equally compelling puzzles that continue to challenge our understanding of this seemingly familiar star. One of the most historically significant of these puzzles involves neutrinos, extraordinarily lightweight subatomic particles produced in enormous quantities as a direct byproduct of the fusion reactions occurring within the Sun's core. Because neutrinos interact so weakly with ordinary matter, they pass almost entirely unobstructed through the Sun's dense interior, escaping directly into space within seconds of their creation, unlike the photons whose slow, obstructed journey outward we traced in an earlier chapter. This property makes neutrinos an unusually direct and valuable messenger, offering scientists a rare, immediate glimpse of conditions within the Sun's core, rather than the delayed, indirect information carried by light itself. When scientists first began directly measuring the quantity of neutrinos arriving at Earth during the 1960s, they encountered a genuinely puzzling discrepancy. Detectors consistently measured only about 1/3 of the neutrino count that theoretical models of solar fusion predicted should be arriving, a persistent shortfall that came to be known as the solar neutrino problem. For several decades, this discrepancy remained a significant, unresolved puzzle, with scientists uncertain whether the underlying issue lay with an incomplete understanding of solar fusion itself, or alternatively, with some previously unknown property of neutrinos. The eventual resolution, arriving only around the turn of the 21st century, proved genuinely fascinating in its own right. Rather than any flaw in scientific understanding of the Sun's fusion process, the shortfall turned out to result from a previously unknown behavior of neutrinos themselves, a phenomenon called neutrino oscillation, in which neutrinos spontaneously transform between different types as they travel, meaning that many of the neutrinos generated within the Sun's core had simply changed into a different type undetectable by the original instruments, rather than never having been produced at all. This resolution stands as a genuine triumph of patient scientific investigation, though it is worth noting that the discovery reshaped fundamental particle physics considerably more than it changed our understanding of the Sun itself, a reminder that some of the Sun's mysteries ultimately reveal as much about the broader universe as they do about the star itself. A second significant area of ongoing investigation concerns the sun's roughly 11-year activity cycle, the same cycle governing the rise and fall of sunspot activity that we explored in an earlier chapter. While scientists understand in broad terms that this cycle results from the gradual twisting and eventual reorganization of the sun's magnetic field, driven by the differential rotation we discussed previously, the precise mechanisms governing the cycle's exact timing, and particularly its occasional irregularities, remain incompletely understood. Historical records reveal periods when this cycle has behaved in ways not fully explained by current models, including an extended period during the 17th century, known as the Maunder minimum, when sunspot activity dropped to unusually low levels for several consecutive decades, coinciding with a period of notably cooler climate conditions across parts of Europe. Scientists continue investigating the precise relationship between these extended cycle irregularities and broader climate patterns, along with the deeper question of what specifically triggers such prolonged departures from the sun's otherwise fairly regular activity pattern. Closely related to this cycle mystery is a broader, ongoing effort to fully understand the sun's global magnetic field, an effort that extends beyond simply explaining sunspots and the coronal loops we examined earlier. The precise process through which the sun generates and continuously regenerates its powerful magnetic field, a process scientists refer to as the solar dynamo, involves enormously complex interactions between the sun's rotation, its internal convective plasma flows, and the magnetic field itself, interactions that current computer models can approximate but not yet fully and precisely replicate. Missions like Solar Orbiter, with its unique ability to directly observe the sun's polar regions, continue providing valuable new data intended to help refine these models, particularly regarding how the magnetic field behaves differently near the poles compared to the equatorial regions, more easily observed from Earth's own vantage point. Beyond these specific, well-defined puzzles, the sun continues to produce smaller, unexplained observations with each new mission and each new dataset gathered, a pattern genuinely similar to what we observed throughout our earlier exploration of Mars's own persistent mysteries. Certain unusual, small-scale magnetic and thermal phenomena observed within the Parker Solar Probe's close-approach data continue to generate active scientific discussion, with researchers working carefully to determine which observations represent genuinely new physical phenomena and which might instead reflect measurement limitations or statistical noise within the collected data. Taken together, these unresolved questions serve as an important grounding reminder regarding the true scope of human scientific understanding, even concerning an object as thoroughly studied and as fundamentally essential to our own existence as the sun. Despite millennia of careful observation, centuries of increasingly sophisticated telescopic study, and now decades of direct spacecraft investigation extending directly into the corona itself, the star that sustains nearly all life on Earth continues to reveal new layers of genuine complexity with each fresh generation of scientific inquiry, a humbling pattern that seems, based on everything explored throughout this documentary so far, unlikely to fully resolve itself any time in the near future. Everything we have explored throughout this documentary, from the sun's violent birth within a collapsing cloud of stardust to its remarkably stable, ongoing fusion of hydrogen into helium, describes a star currently existing in the long, stable middle chapter of its own life story. Yet like every star, our sun will not continue shining in its current form forever. Billions of years from now, it will undergo a series of dramatic transformations, ultimately reshaping not only itself, but the entire character of our solar system. Current scientific estimates place the sun roughly halfway through its main sequence lifetime, the extended, stable period during which it steadily fuses hydrogen into helium within its core, precisely the process we examined in considerable detail earlier in this documentary. Scientists estimate this stable phase will continue for approximately another 5 billion years, meaning that the sun we observe today, despite everything we have learned about its complex, dynamic behavior, remains fundamentally similar in its overall structure and energy output to the star that first stabilized following its early, more turbulent formative period, roughly 4.5 billion years ago. Eventually, however, the hydrogen fuel available within the sun's core will become significantly depleted. As this depletion progresses, the delicate balance between gravity and fusion-generated outward pressure that we explored in an earlier chapter, the balance responsible for the sun's long-term stability, will begin to shift. With less hydrogen available for fusion at the core itself will gradually contract under gravity's persistent pull, growing correspondingly hotter and denser in the process, while fusion activity shifts outward into a surrounding shell of remaining hydrogen rather than continuing primarily within the core itself. This shift towards shell-based fusion will trigger a dramatic transformation in the sun's overall size and appearance, causing its outer layers to expand considerably outward, even as its core continues contracting inward. Over a period spanning hundreds of millions of years, this expansion will gradually transform the sun into what astronomers call a red giant, a vastly swollen, cooler star potentially expanding outward far enough to engulf Mercury and Venus entirely, and quite possibly reaching Earth's own orbital distance as well, though the precise fate of Earth itself during this transformation remains a subject of ongoing scientific debate. This uncertainty regarding Earth's specific fate arises partly because the sun, during this same red giant transformation, will also gradually lose a significant portion of its total mass, expelled outward through increasingly strong stellar winds. This gradual mass loss will correspondingly weaken the sun's overall gravitational pull, potentially causing Earth's own orbit to expand gradually outward in response, possibly allowing our planet to narrowly avoid direct engulfment even as the sun's outer layers swell dramatically in size. Regardless of whether Earth is ultimately engulfed directly or merely subjected to dramatically increased proximity to the sun's swollen outer layers, the intense heat generated during this transformation would almost certainly render Earth's surface completely uninhabitable long before the red giant phase fully develops, boiling away our oceans and stripping away our atmosphere entirely. Following this dramatic red giant expansion, the sun will eventually exhaust the remaining hydrogen available within its surrounding shell as well, triggering a further, more complex sequence of internal changes. Because the sun's core, unlike considerably more massive stars, will never reach the extreme temperatures and pressures necessary to fuse elements much heavier than helium, it will eventually settle into fusing helium into carbon and oxygen for a comparatively brief additional period, before ultimately running out of usable nuclear fuel entirely. Once fusion finally ceases altogether, the sun's outer layers, no longer held in place by any outward fusion pressure, will begin drifting gradually outward into surrounding space, gently expelled rather than violently ejected as occurs during the far more dramatic supernova explosions experienced by considerably more massive stars. This gradually expanding shell of expelled outer material will form what astronomers call a planetary nebula, a genuinely beautiful glowing structure of illuminated gas and dust, despite its somewhat misleading name having nothing directly to do with planets themselves, a naming convention that emerged from the structure's telescopic resemblance to a planet's disk when this type of object was first observed centuries ago. At the very center of this expanding planetary nebula, the sun's original core, no longer generating any new energy through fusion, will remain behind as a small, extraordinarily dense remnant known as a white dwarf. This white dwarf will contain a substantial portion of the sun's original mass, compressed into a volume roughly comparable to Earth's own size, an object of such extraordinary density that a single teaspoon of its material would weigh several tons if somehow transported to Earth's surface. Rather than continuing to generate new energy, this white dwarf will simply radiate away its considerable remaining internal heat, extremely gradually, across an almost incomprehensibly long span of time, continuing to slowly cool and dim across trillions of years, a timescale considerably longer than the entire current age of the universe itself. Throughout this entire transformation, spanning the initial red giant expansion, the subsequent planetary nebula phase, and the sun's eventual settling into its final white dwarf form, the broader solar system itself will undergo dramatic corresponding changes. The surviving outer planets, including Jupiter, Saturn, Uranus, and Neptune, whose own extraordinary characteristics we explored throughout an earlier documentary, will likely continue orbiting the newly formed white dwarf, their own orbits gradually expanding outward in response to the sun's own reduced mass and correspondingly weakened gravitational influence, continuing their ancient, patient orbital journey around what remains of the star that first gave birth to them, now reduced to a small, dim, gradually fading ember drifting quietly through the darkness. This entire transformation, unfolding across a timescale of billions of years, offers a genuinely sobering, though also strangely peaceful, perspective on the sun's own eventual fate. The same star that has shown with remarkable stability and consistency across the entire span of human civilization, and indeed across the entire multi-billion-year history of life on Earth, will not continue in its current, life-sustaining form indefinitely, eventually following the same fundamental pattern of birth, stable maturity, and gradual transformation experienced by countless other stars scattered throughout our galaxy. Each following broadly similar physical processes shaped by their own particular mass and composition. Having traced the sun's eventual transformation across billions of years into the distant future, a natural question emerges from this broader perspective, one that shifts our focus outward from our own particular star toward the countless other stars scattered throughout our galaxy. Given everything we have learned about the sun's specific characteristics, its remarkable stability, its particular size, and its carefully balanced energy output, how unusual is our own star truly, when considered alongside the broader population of stars found throughout the Milky Way. The night sky, though appearing to display a seemingly infinite scattering of individual stars, actually reveals only a small, carefully selected fraction of the total stellar population within our galaxy, specifically limited to those stars bright enough and close enough to be visible to the naked human eye. Among this broader, complete population of stars throughout the Milky Way, our own sun occupies a genuinely distinctive position, one worth examining carefully in order to fully appreciate just how particular and, in certain important respects, unusual our own star truly is. The vast majority of stars found throughout our galaxy are considerably smaller and dimmer than our own sun, a category known as red dwarf stars, which account for roughly 3/4 of all stars within the Milky Way. These red dwarf stars burn their available hydrogen fuel considerably more slowly than our own sun, granting them remarkably long lifespans, potentially extending across trillions of years, far exceeding even the roughly 10 billion year total lifespan we traced for our own sun throughout the previous chapter. This extended stability might initially seem to make red dwarf stars particularly attractive candidates for potentially supporting life on any orbiting planets, given their exceptionally long, stable periods of steady energy output. However, red dwarf stars present their own significant challenges regarding genuine habitability, challenges that help illustrate just how carefully balanced our own sun's particular characteristics truly are. Because red dwarf stars emit considerably less total energy than our sun, any planet capable of maintaining stable liquid water on its surface would need to orbit considerably closer to its host star than Earth orbits our own sun. This closer orbital distance frequently results in a phenomenon called tidal locking, where the planet's own rotation gradually synchronizes with its orbital period, causing one hemisphere to face its host star permanently, while the opposite hemisphere remains locked in permanent darkness, a dramatically different arrangement from Earth's own comfortable, regularly rotating relationship with the sun that provides every location on our planet with a predictable daily cycle of both daylight and darkness. Additionally, red dwarf stars, despite their calm, extended overall lifespans, frequently display considerably more volatile short-term behavior than our own sun, particularly during their earlier stages of development, generating powerful, frequent flares capable of significantly disrupting or even entirely stripping away the atmosphere of any closely orbiting planet. A genuine concern given how close any potentially habitable planet would necessarily need to orbit around such a comparatively dim star in order to receive sufficient warmth for liquid water to remain stable. At the opposite end of the stellar spectrum, considerably more massive and luminous stars than our own Sun also exist throughout the galaxy, though in considerably smaller numbers compared to the abundant red dwarf population. These more massive stars burn through their available hydrogen fuel considerably more rapidly than our Sun, resulting in dramatically shortened overall lifespans, sometimes measured in mere millions of years, rather than the billions of years our own Sun has already enjoyed and will likely continue enjoying well into the future. Such abbreviated stellar lifespans would likely prove insufficient for complex life to have the necessary time to gradually emerge and evolve on any orbiting planet, given that life on Earth itself required several billion years of relatively stable conditions before eventually developing into its current, remarkable diversity. Our own Sun, classified by astronomers as a G-type main sequence star, occupies a genuinely fortunate middle position within this broader range of stellar possibilities, massive enough to generate sufficient energy output to warm a planet positioned at a comfortable orbital distance, without requiring dangerously close proximity, yet not so massive as to burn through its available fuel too quickly, allowing it to maintain the kind of long-term, multi-billion-year stability that has provided more than sufficient time for complex life to gradually emerge and evolve here on Earth. Beyond simply its particular size and corresponding energy output, our Sun also benefits from existing as what astronomers call a single star system, orbited by its planets without any additional companion star sharing gravitational influence over the same collection of orbiting worlds. This arrangement stands in notable contrast to binary star systems, where two stars orbit one another, a genuinely common arrangement found throughout the galaxy, with some current estimates suggesting that roughly half of all stars may exist within binary or even more complex multiple star systems, rather than orbiting alone as our own Sun does. Planets orbiting within binary star systems face additional, genuinely significant complications regarding long-term habitability, given that the combined, shifting gravitational influence of two separate stars can frequently destabilize planetary orbits over sufficiently long timescales, in some cases preventing stable, life-supporting orbits from persisting for the extended multi-billion-year periods generally considered necessary for complex life to have adequate time to develop. While certain specific binary configurations can potentially support stable planetary orbits under the right particular circumstances, our own Sun's simpler, single-star arrangement has provided a considerably more straightforward, stable gravitational environment for Earth's own multi-billion-year orbital history. Considering these various factors together, our own Sun's particular combination of characteristics, a stable, moderately sized single star, positioned to provide a suitable, long-lasting habitable zone without excessive early volatility, appears to represent a genuinely less common arrangement when considered across the broader, full population of stars scattered throughout our galaxy. This recognition carries meaningful implications for the broader, ongoing scientific search for potentially habitable planets orbiting other stars throughout the galaxy, suggesting that genuinely Sun-like stars, however common they might initially seem simply by virtue of our own familiar experience, actually represent a comparatively narrower category of star when measured against the full, considerably more diverse range of stellar types found scattered throughout the Milky Way. We have now traveled the full arc of the Sun's extraordinary story, from the collapsing cloud of stardust that first gave it form, through the crushing heat and pressure of its nuclear core, outward across its long, patient inner journey of light, past its restless, granulated surface, into the mysterious, superheated corona above it, through the violent storms and constant winds it sends streaming across the entire solar system, and finally forward. Billions of years into a future that will eventually transform it into something almost unrecognizable. Now, at the close of this journey, it feels right to pause and simply sit with what the sun actually represents, not as a scientific subject to be analyzed piece by piece, but as a single, continuous presence that has shaped everything we know. There's something worth appreciating in how easily we overlook the sun precisely because of how reliably it behaves. We do not marvel each morning at its rising, the way we might marvel at a rare eclipse or an unusually vivid aurora. Its very consistency, the quality that makes it so easy to take for granted, is in fact the same quality that has made every single thing we have explored throughout this entire documentary series possible. Neptune's supersonic winds, Mars's ancient rivers, the delicate chemistry that once may have allowed life to stir within a Martian lake bed, none of these things exist independently of the sun. They exist because a star formed nearby 4.5 billion years ago and has continued shining with remarkable steadiness ever since. Throughout this documentary, we have seen the sun described in two seemingly contradictory ways, and it is worth sitting with that contradiction directly rather than resolving it too quickly. On one hand, the sun is an object of almost unimaginable violence. Its core fuses hundreds of millions of tons of hydrogen into helium every single second, releasing energy equivalent to countless nuclear detonations occurring continuously, without pause, for billions of years. Its corona periodically erupts in flares and coronal mass ejections, capable of hurling billions of tons of charged plasma across the solar system at millions of kilometers per hour. Its magnetic field twists and reconnects with a violence great enough to release energy on a scale that dwarfs anything humanity has ever produced or is ever likely to produce. And yet, on the other hand, this same star has also proven to be one of the most remarkably stable, patient, and reliable objects in our entire cosmic neighborhood. Its overall energy output has remained close enough to constant across billions of years to allow single-celled organisms in ancient oceans to gradually evolve into the full, staggering diversity of life we see on Earth today. Its rhythms, the daily rising and setting, the gradual turning of the seasons, the 11-year rise and fall of its sunspot cycle, have unfolded with such dependable regularity that entire civilizations were able to build calendars, agriculture, and eventually science itself around the patient predictability of its behavior. This is perhaps the sun's deepest and most quietly profound lesson. Immense power and genuine stability are not opposites. They can exist within the very same object at the very same time, each one somehow making the other possible. The sun's tremendous, violent energy output is precisely what allows it to maintain such long-term stability in the first place, held in careful, continuous balance against its own crushing gravity. Without that violence, there would be no light, no warmth, no energy at all. Without that balance, there would be no stability, no billions of years of steady, dependable shining, no patient span of time long enough for anything as delicate and improbable as life to take root and flourish. There's a kind of quiet wisdom in this balance that feels worth carrying with us beyond the boundaries of astronomy itself. We often imagine calm and power as separate qualities, as though something must be one or the other, gentle or forceful, steady or dynamic. The sun suggests something different. It suggests that the deepest kind of stability is not the absence of great force, but rather the careful, ongoing management of it, a continuous, patient equilibrium maintained moment by moment, second by second, across a span of time long enough to make nearly anything possible. Throughout this broader documentary series, we have explored planets shaped by chaos and collision, worlds that lost their oceans, their atmospheres, and in some cases very nearly everything that once made them promising candidates for life. We explored Neptune, windswept and violent at the very edge of the solar system, its storms rising and vanishing within mere years. We explored Mars, a planet that may once have closely resembled Earth, only to lose its protective magnetic field and slowly transform into the quiet, rust-colored desert we know today. In each of these stories, the sun has remained present in the background, sometimes gently warming, sometimes gradually stripping away, its influence extending across every world we have visited, shaping each planet's fate according to its own particular size, distance, and circumstances. Earth's own story stands out clearly against this broader backdrop. Of all the planets we have explored across this series, Earth alone managed to maintain the full, delicate combination of factors necessary for life to not only emerge, but to flourish and diversify across billions of years, protected by its own magnetic field, warmed at precisely the right distance from a star whose own remarkable stability provided the necessary time for that life to develop. It is worth remembering as we conclude this particular chapter of our exploration that this outcome was never guaranteed. It emerged from an intricate, delicate alignment of factors, many of which we have now examined individually across this and our previous documentaries, factors that could easily have unfolded differently, producing a very different, far less hospitable Earth. This recognition carries a certain quiet weight, one worth sitting with gently rather than rushing past. The same sun that has made life on Earth possible continues, even now, to shine with that same careful, ongoing balance of tremendous power and remarkable consistency. Every breath taken by every living creature on Earth, every drop of water cycling endlessly between ocean and sky, every plant converting sunlight into the energy that ultimately sustains nearly every food chain on the planet, all of it traces back, directly or indirectly, to the continuous, silent work occurring within a star we so rarely think to appreciate directly. Perhaps this is why ancient civilizations, long before they possessed any scientific understanding of fusion, plasma, or magnetic fields, still recognized something essential and worthy of deep reverence in the sun's presence overhead. Their instinct, built entirely from careful observation rather than scientific measurement, was not mistaken. They recognized in their own way exactly what modern science has since confirmed in extraordinary detail, that this particular star, shining with such patient reliability above them, represented something genuinely foundational to their own existence, worthy of the deep respect and careful attention they chose to give it. As we bring this documentary to its close, it feels fitting to return, one final time, to the simple, quiet image with which we began. Every sunrise does indeed feel familiar, arriving each morning exactly as expected, exactly as it has arrived every morning across the entire span of human history, and indeed across the entire multi-billion-year history of life on Earth itself. Yet we now understand, having traveled together through the sun's violent core, its long inner journey of light, its restless surface, its mysterious corona, its powerful storms, and its almost incomprehensible future transformation, that this familiar sunrise represents something far more remarkable than its comfortable, everyday appearance might suggest. It represents the continuous, ongoing output of a genuine nuclear furnace, one that has burned steadily for 4.5 billion years, and will likely continue burning for roughly 5 billion years more, sustaining, patiently and reliably, every living thing that has ever called Earth home. It represents a delicate, ongoing balance between overwhelming power and remarkable stability, a balance so carefully maintained that we rarely think to marvel at it directly, precisely because it has never once, across the entire span of human civilization, failed to hold. Every morning, without asking for attention, the sun rises once more. It has done so for billions of years, quietly sustaining every ocean, every forest, every breath, and every life that has ever existed on Earth. Perhaps its greatest wonder is not its unimaginable power, but its quiet reliability, a cosmic giant whose steady light has shaped our world and our story since the very beginning.